I went back with the slides because I got a question to explain how urbanization, why urbanization affects an hydrograph in this way. So why the peak flow is increased and the base time of the hydrograph is decreased. Basically what happens when you urbanize a catchment is that the time taken by rainfall to reach the closure of the catchment decreases. And this is intuitive because the velocity of the flow of water over the catchment increases. Because of course if you think of the water flowing over a roof, it flows quickly. If you think of the water flowing over a field of grass, it's slower. It's slower because you know there is the grass and also part of the water infiltrates. And therefore it takes more time to travel because after infiltration, you know, in the hypodermic flow, the velocity is lower. So this is infinite. Okay. So what happens then? The base time is of course reduced. Of course it's reduced because if the velocity of the flow increases, the time taken by the drops to reach the closure is decreased. Which means that the base time of the hydrograph is decreased. Okay? At this stage, we can conclude that the peak flow increases, and the reason could be, we could get the reason either by mathematical reasoning or physical reasoning. Let me make the mathematical reasoning first. So if you have the hydrograph, if you look at the hydrograph, I said that the volume of water remains the same, okay? Which means that the area below the hydrograph remains the same. So if you decrease the base time, then of course you get an increase of the peak. This is the mathematical consideration. Is it clear? So basically you have an hydrograph, look at the red one. If you compress it, then if you keep the area below the hydrograph unchanged, the peak increases. This is the mathematical explanation. What is the physical explanation? If you have a given rainfall, and it takes time to get to the closure of the catchment, what does it mean? It means that, look at the catchment, and you have a river flowing along the catchment. So, let's suppose that it rains over the catchment. You have some rain in the undisturbed situation, the rain that falls here, that takes a very short time to get to the closure. And this rain goes to the closure maybe in 30 minutes, okay? 30 minutes. If we look at the drop that is falling here, it takes a long time to get to the closure. And then you get something like 2 hours. In terms of hydrograph, what you see is that T over T, after raining, you see some water that gets to the closure, but not much of that. Because, you know, only the water that falls near the closure. And then you have the rising limb, and then you get, after a while, after a long time, the other water getting to the closure. But meanwhile, the water that rained close to the closure is already gone. And so you get an hydrograph that is long. Long and not peaky. Why is that? Because there is no superimposition at the closure between the water that rained here and the water that rained here. Now, let's suppose that the timing decreases. Decreases because there is urbanization. So this one goes to like 10 minutes, and this one goes to like 30 minutes. Now, you see that the hydrograph becomes shorter. So for sure the resulting hydrograph will finish well before. And you have a greater superimposition at the closure between among the different crops. So you get timing where you have several contributions from the catchment that are getting to the closure all together, and then you get a peak, a higher peak. So when you compress the dynamics of the catchment, you get a higher peak. In fact, one way of lowering, one flood mitigation action that people frequently use is to create in a given position along the catchment a storage where they can store part of the water to be released back later on. They are just trying to lowering the velocity of the river flow. They are just trying to increase the time taken by rainfall to reach the closure. Temporary storage is just a way of increasing the timing, the response time of the catchment. You always have to know that a short response time means an high peak. A long response time means a lower peak. It's clear? Perfect.
So is that retention?
With the retention, you have an artificial way to increase the response time of the catchment. And in the undisturbed situation, typically you have a response time that is a physical behavior of the catchment. If you urbanize it, you reduce the response time. This response time is also called the time of concentration. I will define it now. What is that?
If you take into account the first catchment, the large one, yeah. If it's raining more than 2 hours, we will have a peak like that one, or we'll have a smooth,
Okay.
like this one.
Okay, this is, can I postpone this question 10 minutes? Okay? Because I was going to discuss this issue now, because of course it changes depending on the duration of the rainfall. Okay? And this is an important other story that I'm discussing in 10 minutes. Okay? Yeah, one important thing, parameters. Models contain parameters. There was a model, an empirical model written here before. Qt is equal to alpha times RT. Alpha is a parameter. So equations that build a model, they are always parametric in rainfall and off-rain. What is a parameter? Here you can see the definition. It's not easy to identify a definition for a parameter. I elaborated this definition myself, and what is a parameter? It's, first of all, usually it's a constant. Like alpha that I introduced before, usually it's a constant, but it could be a variable. It could be time varying. But let's say that usually it's a constant. And it is in a term that appears in the model equations, which determines the specific form of the equation, but not its general nature. And let me better explain. If you have a linear relationship, fx is equal to a times x, a determines only the slope of this straight line, not the fact that it's a straight line. So basically, a parameter determines the specific shape, the specific form of an equation, but not its general structure. This is my definition. And I think a good example is the straight line. So A only dictates the slope, not the fact that it's a straight line. And therefore, parameters are essential elements, as I said, of a rainfall model, but they don't determine the model structure. They only determine the specific model form. So once that you selected the model, that's it. You have parameters in the model, and if you change them, you don't change the model. You only change this specific form of the model, the specific form. And I hope that the example of the straight line suffices to explain what I mean. So one thing is to change the parameter of a model, one other thing is to change the model. To change the model means that you adopt a completely different method. To change a parameter in a model means that you are just trying to optimize the functioning of the selected model. Like for the case of the straight line, you decide, I want to use a straight line, a linear relationship. And then you find the value of A, which better fits your purpose. But you are not changing the fact that it's a straight line. This is extremely important. Okay, and then let's notice that one problem that we will have to solve is find the best parameter values for a given model. Okay? This is calibration. Calibration means to find the optimal parameter values. And calibration is always part of hydrological modeling, rainfall and off modeling. So calibration will be an essential step. Good. Validation I will introduce later, but you can understand by intuition that it is a way to check if the parameters are correct, are satisfying. Okay, let's skip this. What's this? This is the first rainfall runoff model that was proposed by hydrologists. And there is a fight between Irish people and British people because it seems that this model, the British claim that it was proposed by this guy who was British in 1889, but the Irish say that 20 years before, a guy called Mulvaney, an Irish guy, already proposed it. And we will never know, I think we know basically, because indeed it was proved that it was Mulvaney the first, but he proposed a form of this model that was slightly different. And let me say that this model is very similar to the very simple linear relationship that I proposed to you before. Simply, it assumes that there is a linear relationship between the rainfall and the river flow. And basically the model says that in order to get the river flow, and this is a model that is used only to estimate the peak flow, not to perform continuous simulation. But because, why is that? You could use it also for continuous simulation, but it was proved that it doesn't work. The performances are not good. While for the peak, it's not bad. And basically, it simply says that to get the flow, the river flow, you have to multiply the rainfall intensity times the area of the catchment with a coefficient, dimensionless coefficient, that takes into account the water losses. And this is reasonable, because if you think of rainfall intensity is expressed usually in a length over time. Length is rainfall depth at the given time scale over time. This is intensity. So if you multiply a length over time times a length square, which is the area of the catchment, you get a cubic length over time, which is exactly a river flow, the same dimension of a river flow. The river flow is cubic meters per second, and it's a cubic length over time. And of course, you need to introduce a coefficient in order to account for the water losses, because you have some evaporation, you have some water that infiltrates, and therefore this coefficient is always comprised between 0 and 1. And this model usually works really well. The only problem is to estimate this coefficient, which is called the runoff coefficient. It's a bit of a problem, because you may say, okay, it's only slightly varying because it's between 0 and 1, but indeed the variability is very significant, because if you take 0.3 instead of 0.6, you get half river flow. And therefore, you see, the approximation is really relevant. And, but in this model is still much used for design. And what is the real utility of this model? The real usefulness is that you get a guess. So what I usually do when I want to guess with some criteria, a peak flow, I usually ask to the people, well, what is the extreme rainfall here? What is the intensity? And then I multiply the rainfall intensity, peak intensity, times the area of the catchment, and I get an upper estimate of the river flow. For sure, because if you assume that C is equal to 1, you get an upper estimate. And then usually I take as C a value of 0.5, which is, we could say that it's a typical value in Italy. And then I get the lower estimate, or something that should be closer to. And this is very useful to get a first approximation. And you know, usually rainfall, as I said, it's less spatially variable. So you have the means to know what is the extreme rainfall. For instance, over the flat area here, usually I take a rainfall of about 50 millimeters per hour, 60, 70. And this is, for me, an order of magnitude of a rainfall that occurs for a duration of 1 hour, about once every 100 years. So I multiply this rainfall, 7 millimeters per hour, times the area of the catchment, and I get a first guess, an upper value. And this is useful indeed. It's very useful because it gives a first indication. And, but this is not really a model that we can use in water resources management. It's extremely important that you know it. It's impossible to be an hydrologist without knowing the rational formula, without knowing its limitations and its usefulness. So I want to mention it to you. But let's skip now. But keep into account that this is a frequent question that they may ask at the exam, and I consider it a very simple question. Like, do you remember the rational formula? And what is C? And what are typical values of C? And you just need to say it's between 0 and 1. This is fine. Okay? Sometimes it happens when we go and compare rainfall over a catchment with the river flow. Sometimes it happens that we find C greater than 1. And this means that either we ignore some contribution to the river flow, like snow melt. So sometimes in snow-dominated catchments, you may have a flood even without any rain. Or over snow-dominated catchments, you may have disasters when you have rain over snow. And in this case, even a limited amount of rain can deliver a huge amount of river flow with a C value greater than 1, because there is snow, and this is one possibility. And the other possibility is that the estimation of A, the area of the catchment, is wrong. Either because you didn't follow the divide, or because there are subsurface contributions. This could happen, happens quite frequently. But in principle, if the estimation of A is correct, of course, we shouldn't get C greater than 1. Now, there is one important thing here, which I forgot to say. You may say, what is the rainfall intensity that I put here? And in particular, what is the duration of rainfall that I need to consider? Because I already mentioned to you that short rainfall is more intense, long rainfall is less intense. So you may ask me, should I put here the rainfall for 1 hour, or should I put the rainfall for 1 week? And then, of course, my reply would be it depends on the catchment. And of course, I already told you that for a huge catchment, you have to use a longer rainfall to estimate the peak flow, because the short rainfall doesn't affect the river flow. And I told you that for a small catchment, you have to use a short rainfall. And then your next question could be, give us an indication for the poor river. What is the length of the catchment? I already mentioned to you a couple of weeks, but it's not enough. You may want to know for a catchment of 1,000 square kilometers, what is the duration of rainfall. And the question would be correctly formulated if you asked me, what is the critical duration? This is the term that you must use. Critical duration of rainfall. So what is the critical duration of rainfall for a given catchment? We can prove with theoretical consideration, which I'm not providing to you, that the critical duration for a given catchment corresponds to the time of concentration, which I'm defining now. Next slide introduces the time of concentration. And you see the definition. So let's suppose that we can measure the time that a drop of water takes to reach the closure. I'm repeating it afterward. So let's suppose that we can measure the time that a drop of water takes to reach the closure from the most remote location in the catchment. Remote in an hydraulic sense. So let's suppose that we can measure the time that a drop of water takes to reach the closure from the most hydraulically remote location in the catchment. This is the definition of time of concentration. So let's pay attention to this. What is then the time of concentration? Is the time that if you take the most far location of the catchment from the closure, it's the time that a drop of rain takes to reach the closure. This means that if it starts raining, let's suppose that the time of concentration is 1 hour. This means that if it starts raining and it continues for 1 hour, at the end of this 1 hour, you have all the area of the catchment contributing to the river flow. So this is indeed a critical situation. When you get to the time when all the area that can contribute to the river flow is actually contributing, this is a critical situation. Because if you have a shorter rainfall, it means that you never get all the catchment contributing to the river flow. Because you have the first part of the catchment that starts contributing, but if the rain time is less than the concentration time, it means that when this part of the catchment, the rain here, reaches the closure, the other rain is already gone. So you never have all the catchment contributing if the rain time is shorter than the concentration time, or time of concentration. But once that your rain lasts for a time that is equal to the time of concentration, you have all the catchment contributing. This is a dangerous situation. And you may say, even if it lasts more, it's a dangerous situation. You may say, if the time of concentration is 2 hours, sorry, 1 hour, then if I have a rain that lasts for 2 hours, I have all the catchment contributing. So you may say, even if it's longer, it's critical. I will say, no, 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 because if it's longer, the rainfall intensity decreases. So you don't get worse in terms of area contributing to the river runoff, because you are already at the top of it. But if it rains for more than the concentration time, you have a lower rainfall intensity. So the situation is not as critical as it rains, as if it rains for a duration that is equal to the concentration time. I hope it's clear. This can be mathematically proved. We don't do that. It just suffices to me that you understand this mechanism. So let's suppose that it starts raining, it rains, it rains, it rains, and then you reach a raining time that is equal to the concentration time. You have all the catchment contributing. If it rains more, you still have all the catchment contributing, but with a lower rainfall. Because we know that rainfall, as the rainfall time increases, decreases in intensity. So the critical situation is when you have a rainfall that lasts as the concentration time. And I think that I replied to your question now, okay? Is it true? Did I reply to your question?
Yeah.
Yeah, okay. So when you use the rational formula, I go back one step. The rainfall intensity that you should put here should correspond to a duration that is equal to the time of concentration. And also rainfall should correspond to the given return period. I'm not defining, again, do you know what return period is? Raise your hand, please. Not everybody. Because this... Sorry? Return period, which means tempo di ritorno in Italian. And this is something that I'm not expected to define in this course, but intuitively, I'm not asking this question to the exam. Intuitively, it means that, by intuition, it means that if you have a flood that has a return period of 100 years, it means that it occurs about once in 100 years. And this is sometimes a detail that is given by law. So when you design a bridge, and in water resources management, usually you don't care about return period. But when you design hydraulic work against a peak flow, for instance, the Italian law tells you that when designing a bridge, the bridge should be designed against the peak flow with a return period of 200 years. So you read on the law that you need to assume forcing that occurs once, on average, in 100 years, about once in 200 years in this case. And therefore you should know what return period is. Usually it is introduced in the previous courses, not in water resources management. But I just would like to mention to you what it means by intuition. And keep in mind that there is a more rigorous definition of what return period means. So if you get into your career, that you get a prescription, the design should be done by assuming a return period of X years. You need to go back to your background and study what it means, because it's extremely important. And the rational formula usually is used to estimate a peak flow, I told you. So we don't use it in water resources management. But the fact that it's used to estimate a peak flow implies that you have to define a return period for the peak flow. And when you talk about rainfall, extreme rainfall depends on the duration of the event and the return period. I'm just running through it because I can't really give to you all the background. And this is a background that is usually part of hydraulic works subjects, not hydrology. Okay. So basically, this is the rational formula, and you should know that it exists, but we don't use it in water resources management. Why is that? Because in water resources management, we need continuous simulation, not event-based. This is an event model. We need continuous simulation. We need to simulate for a long time. So the rational formula is not fine for us. Let me just say that the time of concentration, which is so nicely defined, it's impossible to estimate. Impossible. There are empirical formulas summarized here, and here you can see a summary of typical value for the runoff coefficient, and then in the next slide there is a summary of formulas for the computation of the time of concentration. These are highly approximate, highly uncertain. This is something that you must know, okay? And it's not a big problem because it doesn't affect much the estimation of the peak flow. It's more relevant than runoff coefficient. The time of concentration is indeed something that it's important to define a catchment. I would say that it's important to know the order of magnitude. So for this reason I say the Po River about 5 days, and the Hockenheim River is about 15 hours. But it could be 11, it could be 19. It's really something difficult to measure. And also it depends on the rainfall intensity, it depends on many other issues, and then you may say, what is the reason why then people use it? People used it in the past because, you know, they needed to use very simple formulations to compute the peak flow. And therefore, you know, the rational formula is very simple to use, but unfortunately requires, it's affected by a lot of uncertainty. But people used it, and they are still using it, because it gives useful suggestion, useful advice. And this is the reason. The fact that it's an estimation method is uncertain, it's not a good reason not to use it. It's a good reason to be aware that it's uncertain. But once that you are aware, this is fine. Like I use the rational formula every time that somebody asks me, what is your guess for the peak flow? And of course I say, look, my guess is this one, but it's uncertain. Okay? The time area method is the one rainfall runoff model that I used to explain to students, and now I'm skipping it. And what I wanted to tell you, I think these slides are self-explaining, and I would like that you take a look, and keep in mind that, because it's, I think that if you had hydrology in your background, you already considered it. I think it's useful, and you may just have a look at the model structure and skip these hydrographs. This is the relevant slide. You may also skip this hydrograph, or at least skip, look at the first one and skip the others. But I think that it's a useful background for you to know how the time area method works. And especially if you don't know it, I suggest you to look at it. And I don't ask you any question at the exam unless you are really an excellent student, and then I may ask it to you. And so my suggestion is, if you really aim to get an excellent mark in my exam, just look at it. If you don't aim to it, you may skip it. I still say that if you don't know the time area method, you are missing an important piece of your background. And let me explain better why I'm doing this reasoning. The length in time, in terms of hours, of this subject was reduced this year from 60 to 48 hours, teaching hours. And this was done with several considerations that we had to make on the total amount of teaching hours for the students. The workload was considered to be too relevant, and therefore the department, only our department decided to reduce the teaching load for the students and of course the professors. But the problem were the students, not the motivation were the students, not the professor. It was a motivation that was imposed by law. We had an Italian law that basically said that the workload for the students needed to be reduced unless the department was able to grant some quality standards. And therefore our department decided to reduce the teaching load. And the quality standards were related to the opportunity to bring the students over the field. So basically you consider as teaching load also the field experiments, but of course our department didn't have this opportunity for many reasons and also for financial limitations, and therefore it was taken this decision. But it was agreed with the students that the teacher should give some assignment to study autonomously. So the teaching load was reduced, but some simple subjects were agreed to be assigned to the student to study autonomously. And this is why I'm saying, I'm not explaining this model, but please have a look at it, and I may ask it to you if you are excellent. And okay, I think if you want more details on this reduction that was made in terms of number of hours, I can give it to you. Not now, basically, because now we are already out of time. But if you are interested in knowing some more about these quality standards, etc., and the different choices that other departments have done, I know the situation quite well. I cannot say I was not in favor of reducing the teaching load, but still it's an issue that I consider with much care. Okay, so tomorrow you bring the PC, and I will introduce the linear reservoir method. So I will teach at the blackboard for about 20 minutes, and then we make an application at the PC through R of the linear reservoir method. So please bring the PC and keep in mind that it's not just exercise tomorrow. There is a piece of theory at the beginning. Okay? Perfect.